I'm Chet Rideout. I taught here at Berthoud High School, and classes included astronomy.
You know, the Scott Kin of the earlier generation, right?
Yeah, Form 1. But the thing that I enjoyed the most was constructing the star wall there. That star wall is based on diagrams that were in, not Astronomy, but Sky and Telescope magazine, I believe. And what I did is to photograph them in quarters, project them on the wall, and mark where each of the stars was. Then using various bits of data, I found what the color, the magnitude of each star was, as well as the color of each star. And Maita had this great idea of putting up black light along the top and putting up stars that are of glow material. So we've got not only all of the Messier objects up here, but all of the, what are they? Caldwell objects. Caldwell was the middle name of Patrick Moore, and you couldn't have M objects for Messier and also Moore. And so this is what we came up with. It goes from 60 degrees south of the equator to 60 north, and then in that box you've got the projection of the circumpolar constellations. So anyway, it was a heck of a lot of fun. It was also great working with Tom, watching him climb around on the round framework of the dome.
Spider-Man before Spider-Man was there.
That's it.
You were just waiting for him to fall off.
He taught me amazing things on bathroom construction, forming the perfect sidewalk, and all kinds of other things.
What was the hardest thing in building this place?
The round building was the hard, wasn't it? It was murder. Of course, I also thought he was going to fall off the roof.
Thank you, Chad. Well, I'm the only one of the originals who's still here. They got out while the getting was good. You wind this machine up and then watch it run. This is the piled higher and deeper room. I remember being down in the foundation, and I was forming the round part of the foundation for that dome, and I looked over, and there's Dr. D. Sherrill, and there's Dr. Chet Rideout, and I was the only one without a doctorate. I don't know how they let me in here.
Because you knew how to build things.
So this is one of these absolute dreams, because I remember at the time thinking, my God, will we ever get enough money to actually create the building? And at Berthoud National Bank, it's changed names 4 times, they put the Tinsley in there, in the front area there, and started soliciting for funds. It was a marvelous thing. The genius, the true genius, was Tommy Melsheimer. There's no question. The guy can either do the physical elements or he can do the computerized version. It just blows your mind. Without him, we wouldn't have this. So all that's lovely, and according to that little blue strip right there, the fire department indicated, hey, this is a little too popular. You need to expand the building. We didn't meet fire code, so we doubled the building, and yes, we have a square dome. Yeah, we're slow, but we learn. So what I want to tell you is, it's the people who keep it running who got 76,000 people through here. and changed their lives. I'll tell you one quick story. When we designed this, and some of you have heard this before, I spent hours and hours and hours up at Foundation Engineering with a guy by the name of Kevin Patterson, no relation. And every time I walked in there, the same thing happened. He dropped everything he was doing. He got his best engineer, a guy by the name of Field, and into the conference room, paying customers, who cares about them? And we sat down and we finally got something that worked that we could afford for the foundations, because as you know, there are separate foundations between the building and the two telescopes. They have to be separate. And I finally said to Kevin, I don't get it. You drop everything? You're not getting paid for this. I can't believe the treatment. And he said, well, I got to admit, when I was a kid, I was a druggie. If it hadn't been for math and science, I wouldn't have made it. That was the hook. And that has always been the motivation and the idea for having what we have here today. And it's working. When you get full ride scholarships for kids, holy cow, it's you who did that, the volunteers. And I can't tell you how grateful we are to you for really making this function. Maita is a gift, an amazing man. I love to argue with him. We did it again today. So, bless you and keep up the good work.
Very good. And after you finally get the stamp, the engineering stamp on the drawing, and everybody approves it, Tom threw away the drawings. He says, now we're going to build what we really want. And that's the building. I think the originally design had windows on the north, right? Instead of on the south. So that is how we built it, basically based on what he had in his mind. And it's still the best observatory ever. Still better than the one in Estes Park. We couldn't win the fight there. We had a conventional architect there that made a nice regular roof, and they don't have a great star wall there, so unfortunately. Anyway, again, thanks to all the volunteers. This is still a perfect place, and I'm very happy to keep working here until whenever. Anyway, Andrea, why don't you introduce Phil?
No, actually, I wanted to say a couple words, and then Jay wanted to talk about the radio telescope. So I just wanted to echo what the founders have been saying. I'm a professional astronomer by training, and I go to American Astronomical Society meetings, and I have a very unique niche there because while I've done some consulting work for NASA, I've done various things. As far as I know, there is no other observatory with the quality of the telescopes, with the amount of outreach that we do, the number of K-12 kids who come to visit, and it's all done by volunteers. And I wish I could show you the expressions on people's faces when I'm at professional conferences and they start grasping the magnitude of all that we do here, and they say, but who runs it? Who's paid to do it? And I said, no, it's all volunteers. It was volunteers who designed, who built, who are here so many evenings, and there's just so much heart and soul that goes into this place, and it makes it very, very special. And finally, in addition to the optical realm of our telescopes, we're expanding into the radio realm, and I wanted to invite Jay to say a few words about that.
Thanks. I'll try to make it brief because I know everybody wants to get on to the main program for the evening. Let me start at the beginning. at least for our family. When Catherine and I brought our son to this town, we moved here in the mid-90s, there was no LTO. And we really felt a loss because our family had been connected with observatories every place we lived until we came here. Our next door neighbor in Milwaukee had been the executive editor for Astronomy magazine, so we got a complete exposure to astronomy there. And prior to that, I headed a maintenance program at an astronomical society observatory in Sacramento. So when we came here, we looked around, there was nothing nearby, and so we got on with life. One day, our son Kevin came home from school and said, you know, Dr. Rideout, my science teacher, told me that there was a work project this Saturday. We're going to build an observatory in town. And he gave me a chance to volunteer, and I said yes. So I said, well, how much extra credit are you getting? And he said, you know, we didn't talk about that, but he said it's going to be really good. And then the next day he came home and he said, you know, my English teacher, Mr. Patterson, also is going to be over there working, and he's encouraging the students from the class to go over. So I'll be there on 2 Saturdays now. Well, I'm not sure how many Saturdays it worked out, but our son Kevin really developed a love for working with Habitat for Humanity, because many of the people who did the volunteer work building here were also Habitat volunteers. So what a tremendous way Dr. Rideout and Tom Patterson had of involving the students and making this place theirs from the very beginning, before the first nail was driven in the first piece of wood. And from then on, this has been a community effort. So about 5 or 6 years ago, after one of the board meetings, Glenn and Edna Hetchler and Minta and I were sitting around discussing, I wonder if there would be any possibility of adding a radio astronomy program to this absolutely outstanding optical facility. And Minta said, just in passing, well, by the way, one of my neighbors is a pretty well-known scientist in the field, Dr. Terry Bullitt. Maybe you could talk it over with him and see if he has any ideas. So we did, and boy, what wonderful ideas between Terry Bullitt and another volunteer, David Eckhart. The very first year we had a radio astronomy program, even before we got our big dish running, they had mentored a summer STEM program for students here who made an original discovery, managed to get published in a respected journal with their findings, were invited to a world conference on radio astronomy, and very literally disrupted the conference because of their sharing of information that nobody had ever published before. It was just amazing for high school students to do that. A poster of their project is up on the wall up there. And then just this past summer, Terry worked with another STEM group, this time working on investigations of events in and around the black hole at the center of our galaxy. And there are some small printouts up on the wall there. Terry is in the back row back here. If you have technical questions, ask him, not me. But the radio astronomy program has brought the observatory some tremendous credibility in the community. We hosted a national conference here this summer, or this spring actually, in March, and it has brought us some incredible volunteers. Ted Klein, also in the back row, is a very good example of that. So all that resulted just from this place being here, being an opportunity for people of like mind to come together and brainstorm what else can we do.
Even if they work in different frequencies.
Yes, even if they work, you know. Yeah, as Terry and Ted and Glenn and Edna keep pointing out to people, radio astronomy is looking at exactly the same sort of thing we look at with the telescopes. It's just in a different color. And literally, that's what it is, using different equipment, but pretty much the same techniques. Thanks, Andrea.
Well, one of the most fun parts of helping to run the observatory is our public night, Star Night speaker series. And as we were embarking on plans for our 20th anniversary, we talked about having a special Star Night speaker, but then we thought, you know, we'd rather have a smaller, more intimate gathering just for the volunteers. And we were brainstorming, trying to think who would be the right speaker to invite. And Mainta and I both thought of Phil. Mainta had met Phil at a conference, and I can't even remember where I first met Phil. We've been friends and colleagues for decades. And Phil, yeah, yeah, I am. And Phil is a wonderful writer and consultant on all kinds of science programs, and so we're very fortunate that he was willing to come out here and give our 20th anniversary presentation and meet with all of you. He got his PhD at the University of Virginia, and then went and worked for the Hubble Space Telescope. Then he was a professor at Sonoma State, and now he does all kinds of incredible things. He's written a fun book to read, Death from the Skies, which if you want to learn about all the things that can happen if there's an asteroid impact on Earth, that's the best one to read. And
it's just the first chapter, too.
Yeah.
And they get progressively worse as you keep reading.
And then Hollywood started counting on him for being the scientific expert for all of the asteroid movies. And he has written for Astronomy magazine, for Discover magazine, and now you're writing in association with the Sci-Fi Channel, and I'll just, if I keep on going, we'll never get to hear your talk. So, Phil Plait.
There we go. This is sound technology, not optical technology, so I don't know.
You will push the button when he needs.
On prom later. How's that? Can you all hear me?
Yeah, it's
fine. Excellent. Okay. Thank you, Andrea. Thank you, everybody, for having me here. I'm embarrassed that this is my first time here. I live in Longmont, and not just Longmont, but sort of northern Longmont. Not really. I'm out in the country. But, you know, I could walk here in about 2 hours, I think, so this is silly that I've never been here before. But rest assured, at some point, I'll have a volunteer give me 5 or 10 minutes on the 24-inch so I know how to use it, then I'll kick them out.
You're on.
Yeah. You know, I've been around a while, so yeah, I mean, it's funny to think about all the different magazines and stuff I've read before. But it's taken a long time. But in the meantime, I think I've probably spent more hours behind the eyepiece than I have in front of my keyboard. So it's always nice to come to an observatory, and I don't covet that 6-inch astrophysics at all. So I've heard you've had some exoplanets talks this year. That's great because they'll lead into mine, and mine will be better. So I can't say that. I know they were by professionals, and I'm more of an enthusiastic bystander when it comes to exoplanet discoveries. And I remember when the first one was discovered around the pulsar, and then they started finding them around sun-like stars, and then one day it occurred, then when they started translating, and I'll talk about all this in a minute, but I realized a 14-inch telescope could detect these. These have been in front of us this whole time, and nobody thought to look for them this way. And I was at Sonoma State University. We had a 14-inch, and I thought, we should do this. And then it turns out it's actually doing it is harder. Oh gosh, I have to like write software again. No, there's a reason I left Hubble. I'm a terrible programmer. So all of this is from an enthusiastic astronomer who just loves this stuff. People ask me all the time, what's the coolest thing going on in astronomy right now? And it's like, oh sure, gravitational waves from emerging black holes. Ooh. No, so we're finding these planets, come on. I've been watching Star Trek since I was a kid, which is why I've got The Strange New Worlds as the title. When you find something for the first time, in astronomy especially, it's going to be weird. It's going to be the brightest thing. It's going to be the easiest thing to find. It's doing something spectacular. That's why you see it first. And then you go, hey, here's this thing. Maybe there are more things. And that's exactly what happened. We've been finding more of these planets now. Last week, I think, they found the 4,000th confirmed exoplanet, an alien planet orbiting an alien star. 4,000 of these things. That means you can categorize them. You can start to look at them, figure out what they're doing, put them in different bins, like these are big ones, these are little ones, these are around big stars, these are around little stars. I call that zoology, right? Because what do you do when you see an animal? You think, well, it has 4 legs and fur, and it doesn't fly, and it's viviparous. I know that's a biology word, I don't really know what it means. But, so you can start categorizing animals that way, comparing and contrasting, and that's how people learn about these things. And we can do that now with these planets. We know enough about them that we can start saying to ourselves, how are they grouping themselves? What are we seeing here? What trends are we seeing? What trends aren't we seeing that we thought we would be seeing? That's important, and I'll get to that. And the whole time, what are we looking for here? Well, we're looking for science, right? We just want to learn about all these things. Come on, we're people. We're humans. We want to find another Earth. We want to know if there's life in the universe. And before we can look for weird things, we have to look for things like us, because we know life worked on Earth. We don't know if it works on other planets. So look for planets like Earth. That's the best place to look first. So the question naturally arises, is the Earth special? All of these planets we are finding are a little bit weird. They're not like the Earth. So is our planet special, or is the galaxy filled with them? And it turns out, I have the answer for you tonight. I will give you a spoiler alert. The answer is yes, no, maybe. It's complicated. Pick 2. I don't know. It turns out, yeah, the answer to this question depends on what you mean by the question. And let me tell you something that is always the case. We like to think we know stuff. Pluto's a planet, right? I don't think so. But you might. And I argue that it depends on what you mean by planet. And it's the same thing here. Is the Earth special? Depends on what you mean by special. Recognize that? That's a planet. That's Earth. I like this shot. This is from the Discover satellite, which is orbiting about 1 million miles towards the sun, and is turning its back on the sun, looks at the Earth, and takes a picture every few hours, I think, and you get these gorgeous shots like this. This is a cool shot. Normally you see, North America, South America, and all that. I feel that we're biased living in the U.S., so I kind of thought I'd open with this shot. I love this. And even from 1 million miles away, you can see the Sahara Desert, the Savannah, Middle East, Europe. These are pointed here, right? Yeah. Let's see. I think there's just I don't know if you can see the United States here. This is not really a representative picture of the Earth, though. A better picture of the Earth is this one. That's Earth. Okay. You might not recognize that. That is the Pacific Ocean. The Pacific Ocean is really big, and it's really hard to know that until you fly over it. I flew out of San Francisco to Australia, and in 5 minutes we were over the Pacific Ocean out of SFO. And it was like 13 hours later we flew over the coast of Australia. It's really big. It's the entire hemisphere. You can see up here, there's the US. In Mexico, there's Baja California. Here's Australia, right? That's really it. on this scale, again, Hawaii's in there someplace, I don't know, somewhere. This is Earth. And what is Earth? Earth is water, on its surface at least. I can't tell you about the core. But on the surface of the Earth is 70% or so water. Moreover, because of our distance from the sun, water can take 3 separate forms on Earth. And that is, it's water, it's liquid water, but you can see the white of clouds here, and then down here in Antarctica, it's frozen. So it's in 3 separate physical states, gas, liquid, and solid. And that's important, it turns out. Water is really good as a medium for life. If you take water and throw glop into it, shake it up and add sunlight, and wait about 200 or 300 million years, you get little critters in there swimming around, algae and whatnot, plants. And then, wait 4 billion years later, and here you are listening to me talking about it. So, water is a really good thing for life. Are there other things for life? Maybe. Maybe. We don't know. But certainly water is the thing to do. Of all the planets in the solar system, not to scale. Actually, the sizes are to scale in here, but not the distance. When you look at the solar system itself, and I'll get to water in a second in the solar system, and you look at it and you say, okay, just kind of defocus your eyes. What do you see? You see 4 little planets and 4 big planets, and nothing out here again. This is a graphic I found on the web. I love talking about Pluto being a planet or not. I literally don't care what people think if it's a planet or not. But I love teasing people who swear it's a planet. And if I can just wind them up a little bit, it's just one of the few pleasures I have in life these days. So I do that sometimes. Ignoring Pluto and those objects for a minute, because we'll get back to them. And by a minute, I mean really closer to 30, but we'll see. There are 4 rocky inner worlds, 4 gas giants on the outer part. There are planets like the Earth here, Mercury, Venus, and Mars, although they're smaller, hotter, colder, whatever, thin, thick atmosphere. The question then, when you look at this, is are there other planets in our solar system like the Earth? And the first thing you think of is Mars. Well, maybe. Mars, well, it's dinky, its atmosphere is really thin, it's all carbon dioxide, it's really dry, it's cold. It's just a terrible place to live. I don't know what Elon Musk is thinking. And you say, well, Venus is about the same size as the Earth, has about the same mass and gravity as the Earth. In fact, it has about the same amount of carbon as the Earth does. But while we keep ours stored in the rocks, which is a good place to keep it, Venus keeps it in its atmosphere. So it's extremely hot on the surface of Venus. And it's hot enough to melt zinc. I know that's a weird thing to say. But it's not quite hot enough to melt lead, which is really what you want to say. But it's hot enough to melt zinc, so that's good. Or tin, something like that. I don't know. The point is, it is Earth-like in many ways until you really look at it. And then you realize it's a terrible place to live. It's like 900 degrees Fahrenheit on the surface, 90 times Earth's atmospheric pressure. It rains sulfuric acid. It's awful. It's worse than Colorado in July. So, but no mosquitoes. So, so there's not really anything Earth-like in our solar system right off the bat. But the question is, are there other solar systems? And if there are other solar systems, do they have Earths? And do these solar systems look like ours? And I am getting over a sinus attack that was epic, so pardon me, my throat's going to get dry here. I'll probably start coughing and wheezing later too. So, all through the 20th century, people were looking for planets around other stars. A lot of techniques they were using, a lot of false alarms. I remember back in the day when they thought there were planets orbiting some nearby stars, and it turns out they were retracted, like the 1970s. And then in the 1990s, we started finding planets. The way we found them was a weird method, which I'll get to in a minute. I'm not going to talk about the first method. I'm going to talk about the best method that we have right now, and that's the transit method. Is anybody here not familiar with this? I just want to know how much detail I need to give. You all, does anybody else want to give the talk? I mean, it's up to you. What I'm doing here. Can you start the animation, please? Just click on it, because I can't do that from here. So super briefly, right? And a star. And you have a planet, and it orbits the star. When it blocks the star, the light drops. That's all that graph is telling you, right? The star gets dimmer. This is a ridiculous example. I don't think you get planets that big around stars that big. But still, it's just an exaggeration for effect. Your observations, there's always going to be noise in them, but then you can fit a curve to that, and you can figure out things like how big the planet is. You know how big the star is, you know how big the planet is, because if it's blocking 1% of the light, that tells you how big the planet is compared to the star. There's some neat things going on in this. The planet's undergoing phases, like the moon does as it goes around the Earth. And in some of these light curves, you can see that. You can see that it's at the start, the amount of light is dropping before the main transit, because that planet, as it comes around the stars, is basically new, like the new moon. And I remember when they first, it was Kepler, Kepler Space Telescope, looked at one of these stars that we knew had a big planet around it, and you could see that in the light curve, and I lost my mind. I thought that was the coolest thing I'd ever seen. This is a great method. The problem with it is that it only works if you're seeing this orbit edge on, right? If the planet's orbiting face on, you don't get this. It has to be edge on. It works better for planets that are closer in, because the closer they are to the star, the more likely they are to block it. If they're really far out, it only takes a little bit of a tilt of the orbit, and it doesn't block the star. There's a lot of disadvantages with this. The advantage of this is that a planet like Jupiter, let me do it this way. There we go. A planet like Jupiter will block 1% of a star like the sun. And a 1% drop in light is piece of cake with telescopes. Easily do that with a small telescope and an off-the-shelf hammer. So this method works really well. It's how we found most of our planets. The way we first found planets, though, was with the reflex velocity. Are you familiar with this? Of course, everybody's going to, if you don't know, nobody's going to say, yes, I do not understand that, because nobody ever wants to volunteer that information.
I'm not familiar with the reflex.
Excellent. You will make a fine scientist. It's the scientist who goes, wait a minute, I don't get this. You got to be able to learn this stuff, right? So, basically, when you think about a planet orbiting a star, the star has all the mass, the planet has very little mass, and so it's just circling the star. The star's gravity is making that planet orbit it. But in fact, the planet has some mass too. So it's not that the planet's orbiting the star, it's that they're both orbiting their center of mass, what astronomers call the barycenter. So if you have a star here and a planet, as the planet goes around, the star is making a little circle while the planet makes a big circle, and they're on opposite sides of the center of mass. The easy way to think of this is a seesaw. If you have a seesaw and two kids with equal weight, you put the fulcrum right in the middle, right? That balance point's in the middle. But if you put 3 or 4 kids on one end and 1 kid on the other, you have to move that fulcrum closer to the heavier part. So the barycenter is always closer to the more massive object. It's exactly the same physics, except you have rotation in this one, which makes it really hard. If you see this edge on, you see this situation on the right, and being able to actually see a star move back and forth because of a planet's orbit is almost impossible. I say almost because, in fact, it's been detected in a couple of systems, but it is super hard to do. Like, it's only been done with a couple of stars because it is an incredibly difficult observation. However, we have the Doppler shift to help us, right? When something's moving towards you, it's blue shifted. When it's moving away, it's red shifted. Just like when a motorcycle drives past you on the street, it goes, right? That pitches up high when it's heading toward you, and then it drops when it passes. Because, technically, the wavelengths are getting squozed, I believe is the correct term. When it's heading towards you, the waves are getting squished together, and that makes the pitch go up. And when it goes past you, the waves get stretched out, and the wavelength gets longer. It's the same thing with light. So when the planet's heading towards you, as the star is heading toward you in its little orbit, its light is blue shifted. When it's heading away from you, the light is red shifted, and that can be measured. And in fact, we can measure this to such a small number that I'm still kind of stunned by it. Some of these stars have this reflex velocity that's like, it's a velocity in response to the planet's velocity of meters per second. Like, this star is going around in a circle like as fast as you can jog, literally this fast. So it's amazing that we can measure that. Now look, I'm on the other side of the room. Just trying to keep you all the way. This can be done. This is how the first planets kind of were found. The first planet was found around a pulsar, but we started looking at nearby stars that were bright, looking for a periodic Doppler shift in the star that wasn't caused by its rotation, that wasn't caused by some star in the background messing things up, it wasn't caused by star spots. And at first, when the first ones were found, they didn't believe it, which is the correct thing to do, is to say, yeah, prove it. You've shown me something interesting, now prove it. And they kept finding more and more of these things, and then one day, one astronomer said, you know, we think that this planet is orbiting, that we're in the plane of that planet's orbit. So I predict that it will transit the star, and we'll see a drop in the starlight by about 1% at this time. And it happened. And it was like overnight. All the astronomy community went, we believe you. that was a good day. So combining these two things is great, because the transit method tells you how big the planet is. The reflex velocity method tells you its mass. Because the more massive a planet is, the harder it tugs on the star. And that tells you, and if you have the mass and the size, that tells you the density. And the density tells you what it is. If it's iron, if it's rocky, if it's mostly gaseous, you get wildly different densities. So you can learn a huge amount about planets if you can combine these two things. So we've been doing this from the ground for a long time. The Kepler Space Telescope did this for several years, found thousands of planets. Kepler is now kind of winding down. The TESS, which I believe is one of the speakers came here and talked about, the Transiting Exoplanet Survey Satellite. I always have to think about that when I'm doing it in my head. TESS is wrapping up its first year of staring at different spots in the sky and looking for, it looks at thousands of stars and looks for these transiting exoplanets. And they just announced it just found its smallest planet so far. It's a little bit smaller than Venus. So that's really cool. The smallest planet Kepler found was smaller than Mercury. So we still have ways to go to find small planets. I'll talk about that in a second. So we're doing this. We're actively doing this. Those are two ways to look for planets. The third way, and let me tell you, there are like 7 or 8 different ways of looking for planets, and they get weirder and weirder the more you look at them. But this is the way I like, as an observational astronomer, and that is finding them next to the star. There's a blip of light next to that star. That's a planet. And this has been done. Oops. Here we go. Beta Pictoris is a southern star. It's a very bright star. In these images, it's been blocked out, and they put a little star thing there to let you know where it is. And when they did that, right next to it was this blur of light, which we know is the exoplanet Beta Pictoris b. The planet's always given a lowercase b, the first one found, and then they're lettered in order. This was taken in November of 2003. 6 years later, this image was taken. Here's where it was in 2003. Here's where it was in 2009. That's because it's orbiting the star and was 6 years later on the other side of the star. And you see that. And then the bottom image, taken a year later, it had moved a little bit more, and it was here. Here's where it was in 2009, here's where it was in 2003. This destroyed me when I saw it. You don't see things moving in astronomy very much. If you take a picture of the Orion Nebula now, wait 10 years and do it again, it's going to look the same. The Crab Nebula doesn't. You can actually see that expand, which I love. But something like this, to see a planet orbiting its star, is so thrilling to me. This is preferentially done with young stars, because a planet like Jupiter and a star like the Sun, there's a bit of a contrast problem there. If you're looking at reflected light, Jupiter's reflecting sunlight. If you're on Alpha Centauri and you're looking back on our solar system, the Sun is about 1 billion with a B times brighter than Jupiter. Back in the day, I was trying to think if we could look at Alpha Centauri to see if there was a planet like Jupiter orbiting it, and it turns out that contrast ratio is a little bit of a problem. 1 billion to 1 turns out to be difficult. But if you do it when the star is only a few million years old, and you look in the infrared, stars don't put out as much infrared, typically, so that's a good place to look. The star isn't as bright, but the planets are still hot. They're young, they're still forming. And if you think about the way people say, why are planets hot when they're young? And I say, imagine you're on the Earth and an asteroid 20 miles wide slams down in front of you, right? How much energy is released? unbelievably hot. Now, have that happen every day for about 50 million years, right? That's why young planets are hot. This is how they form. So these things glow in the infrared. And so you're making the planet brighter and the star dimmer, and then you can use something like Gemini or one of those big infrared telescopes, block out the starlight, and the planet pops right out. And we've done this many times, and by we, I mean professional astronomers, not me. But I like to think I'm still kind of standing outside that circle, kind of looking at them going, you go, good job. HR 8799 is another awesome one. This is a low mass star, not too far away, I can't remember the exact distance. And it has 3 planets, B, C, and D. Again, these are named in order of discovery. And this is where they were in July of 2004. The star has been masked out, and you can see all 3 of these planets. In fact, it has 4 planets, including E, which is dimmer and hard to see. But here it is in this image up here. It was discovered later. Now, can you click on this to make this animation go? And the beauty of this is that if you wait and take observations every month or 2, you can actually see their motion as you watch. Okay. This is actually, I think it's like a half dozen observations, and they've done some what's called tweening, some interpolating to make the motion smooth. But if you didn't have that, they would just jump around, but you can still see that motion. And that's a solar system that you're watching from a distance, and the planets are going around it. I think that's just about the coolest thing ever. And so that's the kind of thing that we're doing now.
So is the plane of that solar system, are we looking at it from straight on?
Pretty close, actually. Yeah, these planets are making, I think they're making ellipses, but you can determine if how circular their orbits are. There are a lot of ways of doing that. But yeah, I mean, this is just one. We wouldn't be able to see a transit with this one because we're basically seeing it, if not face on, then at some sort of angle like that. Yeah.
From the brightness received, can we tell what color the object is?
Yeah.
Jupiter's kind of brown, you know?
Oh, well, you can do that in the infrared because these aren't optical colors. But the beauty of doing it infrared, too, is that then you can say, we know how old this star is. It's part of a cluster of stars that are young, that are forming. And we can guess their age at like 2 or 5 or 10 million years or whatever. And then you look at infrared colors, and you can match that to a spectrum of a star, like a brown dwarf or a very low mass dwarf. When planets are young, they're hot. And so they glow with the spectrum of a star that has a lot more mass. Eventually they cool off. It's complicated. But by looking at the colors and knowing the age, you can determine the mass of the planet, roughly. So even though we can't see it tugging on the star, by looking at the colors of these planets, we can determine they're like 3 times the mass of Jupiter or whatever. And that to me is phenomenal too. This is all magic. Yes?
Maybe I just missed it. What are all the other lights circling the star that aren't planets?
Yeah, noise. Basically, these are exposed. Like that right there. That's just a little blip. Like all this is just noise from the star. The star has been blocked out. They're also using adaptive optics, which is changing the shape of the mirror to make the star as focused as possible. And when you do that, you get all kinds of weird effects, plus diffraction effects like the airy disk. Have you ever seen when Hubble takes a picture of a star, there are rings around sometimes those stars, and that's an optical effect. It's not real. So that's just noise in the image that you can ignore. And you know it's noise because it's in one image and not the next. Whereas the planets are persistent. They're always in every image in the same spot, or roughly in the same spot. You can trace their motion. Great. These are not going to be Earth-like planets. These have to be big so that we can see them in the infrared. And also, by the way, they're glowing hot. So it's like looking down a volcano, except it's a whole planet. So, you're not going to see little green men there. But it's nice that we can do this and see these planets. So this brings up the idea of the habitable zone. This is for Pirates of the Caribbean fans, this is not a rule so much as a guideline. Anybody really? You remember that? Hardly? Never mind. It's an old movie. The idea is that for a planet to be something like the Earth, we want it to have liquid water on its surface. If we have liquid water on its surface, it can't be too hot, it can't be too cold. So if it's too close to the star, all the water will be boiling off, and if it's too far, it'll be frozen. It depends on a huge number of things. It depends on the star. It depends on what's in the atmosphere of the planet, right? What chemicals are in the planet. So you can't just say something in the habitable zone is habitable. In fact, Venus is on the inside edge of the habitable zone for the sun. If it had an atmosphere more like Mars, it would be more Earth-like, bizarrely. But its thick atmosphere means it's really, really hot. Mars is on the outer edge of the habitable zone, but its atmosphere is really thin, and so it's really cold. If you could swap Venus and Mars and wait a billion years or two, we could have 3 habitable planets in our solar system. But it didn't work out that way. So, this isn't a rule, it's just a guideline. Some people call this the Goldilocks Zone. I think that's what it was first called, just sort of colloquially, and then we changed it to habitable zone, which is much tougher to say and spell. I will say I never liked the Goldilocks Zone. It should have been called the Baby Bear Zone, and if you think about it, you'll agree, because, right, it's in the Baby Bear Zone, everything was not too hot, not too cold, it was just right, okay? But of course, we have some, blonde European girl, some colonial chick, walks into the house, takes everything, goes, oh, this is too hot, this is too cold, I'm going to throw these away, this is just right, I'm going to eat it. And then we name it after her. No, sorry. Not going with that, so I like the habitable zone. Didn't think the talk would get political. So around hotter stars, the habitable zone is much wider. It's just the way, it has to do with the way the heat from the star drops off at a distance, and when a star is really hot, you have to be farther out from it to get to the habitable zone in the first place, but the zone itself is much wider. And then for cooler stars, it actually huddles much closer into the star itself. So it's too hot close in, green is good, but it's actually smaller than a star like the sun, and it's much, much, much wider in hotter stars. So weirdly, I remember watching Star Trek as a kid, and they always had, Rigel 5 or whatever, it was some planet. I'm thinking, Rigel's an O star. It's like one of the most massive, awful, luminous, hot stars in the galaxy. This would be a terrible place to have a habitable planet. It turns out, hey, maybe not. Maybe Star Trek had it right. Of course, the problem with that is that it's a very young star. It's only a few million years old, and it's going to explode in a supernova before you get any life on it. So it turns out they were wrong, and I was right in the first place. I'm not going to take that out on Star Trek because I love it so. So the question is, have we found planets in the habitable zones of stars? And the answer is yes. That started happening fairly quickly. They always have this sort of alphabet soup of a name. If they're found by Kepler, and then there's a number which is basically in the catalog, in order. Kepler looked at 150,000 stars, something like that. And as it discovered planets, they would name the stars. This was the first one to find planets, so it was Kepler 1. And then the B for the planet. So Kepler 452b is in the habitable zone of a star that's like the sun, a G star. Got a bunch of K stars, which are a little bit cooler than the sun, and they have a lot of planets in the habitable zone. And M stars, it turns out, are great places. Even though their habitable zone's narrower, they wind up, it's kind of easier to find planets around M stars because they're smaller stars. And so a planet like the Earth blocks more of the light. So even though the star is fainter, you're blocking more of the light with a small planet. So, 6 of one, half dozen another. As a friend of mine used to say, 6.5 of one, half a baker's dozen another. I always love that phrase. So the point is, yes, we are finding them. You may notice, these are just drawings, of course. We have no idea what these planets look like. But the one thing you may notice is that they're all bigger than us. We call these super Earths. Anything between up to about the size of the Earth, up to about twice the size of the Earth. If they're bigger than that, we start to call them mini Neptunes. And it's just a judgment call, which is which. At this point, well, let me put it this way. At this point, we're starting to get to my original question: is the Earth special? And the answer is maybe not. Right? We're finding all these planets in the habitable zone. They're bigger than the Earth, but some of them, even though are much larger than the Earth, if they're made of lighter stuff, like maybe they don't have as much metal in their core, or they have more water or something, they may actually have the same gravity that the Earth does on their surface. If they get too big and they have the same density the Earth does, the gravity gets much larger, much more rapid. But you know, you could live on a planet that had 50% more gravity. It'd suck. As you get older, and I have bad knees and a bad back, I have enough time in low gravity. Being at 1.5, I would, after a while, would be tough. Doing the laundry would be hard, carrying that thing up the steps. That kind of thing. You have to think about this stuff. What?
So,
Yes.
going to your original questions, is Earth spatial?
Yes.
Which kind of leads to, can we find other Earths?
Yes.
If we were to have Kepler or TESS or any of these different methods that we described being run by an alien civilization far from us, will they be able to find Earth?
Yes.
Okay, so
How's that for an answer?
it's an interesting thing because the techniques that are being used are capable to find Earth.
Sure.
But we don't seem to be able to find something that really match Earth.
I will get to that in just a second.
Okay.
Stop being so smart. I am getting there. Yes, if aliens were looking at our solar system and they were using the same techniques we were, and they were smarter than us in that they funded their version of NASA better than we do, and said, gee, you know, we have all these 2.4 meter blanks left over from the Cold War. Why don't we just put these in telescopes and point them at stars? Yeah, you can pick out the Earth easily. But these are Kepler and TESS. These are smaller telescopes designed to survey the sky. And there are space telescopes that are designed, but they aren't funded well to look for Earth-sized planets or other stars. And mind you, all of these planets I'm showing you, this is a graphic about 4 years old. These are all super-Earths. But we have found planets smaller than the Earth. Those tend to be closer into their star. But that's a selection effect. They're easier to see when they're like that. And I'm going to get to that in a second, too. Yes?
Are these gaseous or are they rocky?
Beats me. Your guess is as good as mine. I mean, the answer is, yeah, some of them are probably one or the other. If they're transiting, then that means we can get a good reflex velocity for them. But a lot of these stars are really faint, and the only way to get a good reflex velocity is to use a spectroscope, and then you have to spread the light out. If you're taking a faint star and spreading its light out, it gets even fainter, and then seeing that really small Doppler shift is super hard. If we had funding, you know, if we had Hubble pointing at these things, let me tell you, the first transiting exoplanet, one of the first transiting exoplanets was like HD 209458, actually I think that's right. Jupiter-mass planet, Jupiter-sized planet orbiting a star like the Sun. The discovery of that thing, the data were really noisy. You could see the dip in it, but it was noisy. We observed that with our spectroscope on Hubble, and that was the smoothest light curve I have ever seen. That was glass, just this perfect curve. It was amazing. So yes, you can do this, but you know you need a lot of Hubble orbits, and they're testing about getting those out. So this is starting to lean toward the idea that the Earth's not that special. There are a lot of planets in there. The question is, are they Earth-like planets? That's tougher to know. There we go. Some of these planets get to be a lot bigger than the Earth. Again, these are drawings. These sizes are pretty well known. Up to about the size of Kepler 22b, these planets could still be rocky. The problem is, once they get up to be about that big, their gravity gets strong enough that as they're forming, they start to draw in the lighter gases around them, and they become gas giants. So there's this, it's a tipping point. It's this really sort of narrow range of masses where, yeah, I can still be like Earth if I'm on this side of it, but if I'm on that side of it, I'm more like Neptune. And so that's the super Earth mini Neptune divide. The other way, of course, is you can tell it's a super Earth instead of a mini Neptune if it has a cape. Really? Nothing? Oh my gosh! Wait, what kind of speakers do you usually have here? Like really serious academic types? I'm a smart ass. This is what my talks are like. So this plot, this is a histogram plot. I love this because there's a vast amount of information in this, and it's the only plot I'm going to show you. Really, actually, that's a lie. I got another one. That one's even easier. All this is saying, the only thing you have to worry about here is that this is number of planets that we discovered. This is as of 3 years ago now. So this is like when we had about 3,000 planets, maybe something like that. A bigger graph, a bigger bar means we have more planets like that. And left to right, these are low mass planets, and these are high mass planets. And so right away you say, wow, look at these Mars-sized planets. We haven't found very many. There must not be many out there. So that's not true. They're harder to find because they're small. And that means they don't block as much of their star's light, and that makes them harder to find. There could be 10 times as many of those as any other kind of planet. We're just not finding them. So that's what that's telling you. Earth-sized planets suffers the same problem. They're just hard. We found a lot. We have more of these than the Mars ones because they're easier to find, but we don't know if this is complete. In other words, we may be missing a lot of them. It's an incomplete survey. But then you get to the super-Earths, and all of a sudden, kablam, we're finding a lot of them. And then the sub-Neptunes, the mini-Neptunes here, a lot of them. And this is where the graph gets really interesting. Because then when you look at Neptune, and then Saturn and Jupiter and super Jupiters, planets don't get that much bigger than Jupiter, really. If you add mass, they actually stay roughly the same size because of physics. But if there's a Jupiter orbiting a planet, we're going to see it in the transit method. That's the easiest thing to find. Boom, big drop in the light curve. So this is probably complete. If a planet transits and it's Jupiter-sized, we've seen it by now in the Kepler survey. And yet, we're not seeing anywhere near as many as these sub-Neptunes, which we could miss a few. But even at sub-Neptune size, we should probably detect it. So this is telling you something physical, that there are a lot of super-Earths and mini-Neptunes. And in fact, those are the most common kinds of planets in the galaxy. We've looked at enough stars to know that statistically, that the universe is super good at making planets bigger than us and smaller than Neptune. That's odd. How many planets in our solar system are bigger than Earth and smaller than Neptune? Zero. None. Unless planet 9 exists way out past Neptune, and that might be a super Earth, but we haven't found it yet. And even so, that's kind of an oddball. That's way out. We're finding these close into their star, like with other planets in the solar system. So the universe really likes to make planets that aren't like the Earth. Uh-oh, that's pushing the question the other way now, right? Lots of planets in habitable zones, but we don't make that many planets like the Earth. And that's interesting. It's a big question in physics right now is why they're so much easier to make. And a lot of models are trying to explain that, a lot of physics models. And I don't think that's really been answered yet, necessarily. We have some ideas, but they're still working on it. So we're going back and forth here, right? This is why I was telling you, are Earth-like planets common? Well, it depends what you mean, by common, and what you mean by they're special. There are planets orbiting their stars where there could be liquid water on the surface. There don't seem to be that many that are the size of the Earth. They tend to be bigger. Well, maybe Goldilocks was too picky. We know she was picky. I believe the term is high maintenance. But, and I don't mean that in a sexist way because, oh my, I hear it from my wife when she's cooking because she's a great cook. And I'm like, yeah, I don't like this. And she's like, oh, you're such high maintenance. Was Goldilocks too picky? This is an interesting question. Do you need to have liquid water on the surface of your planet for life? And the answer is maybe not. You go to Jupiter, and Jupiter is the last place you would look for life in the solar system. This gigantic planet, 11 times wider than the Earth, 300 times the mass, an atmosphere 3,000 miles thick, doesn't have a surface, huge magnetic field, all that stuff. But it's got these moons. Now, Io is eruptive, volcanic, the most volcanic object in the solar system, spewing out sulfur. It's a really, really terrible place. But then there's Europa. And even in the 1970s, scientists were starting to think, Europa is made of ice. We know this. It's very reflective, very shiny and white. As it orbits Jupiter, it's slightly elliptical orbit. So sometimes it's a little bit closer to Jupiter, and sometimes it's a little bit farther away. And gravity depends on your distance to an object. So I'm feeling a certain amount of gravity from, and it's Andrea, right? That's how I've always pronounced it. Or do you go by Andrea?
I go by Annie.
Okay. So Annie, yeah. So Andrea has got a gravitational pull on me. But my front side is closer to her than my back side. So my front side's pulled towards her a little bit more strongly than my back side. That's tides. That's what we call tides. It's just a change in the force of gravity over distance. And so something like Europa is experiencing huge tides from Jupiter because it's super massive. It's got a lot of gravity. So the near side of Europa is pulled much more hard than the far side. And not only that, but because it's changing its distance just a little bit, it doesn't take much with Jupiter's star gravity, the amount of gravity it feels changes every orbit. And so it's being stretched and compressed and stretched and compressed. If you've ever taken a wire coat hanger and bent it back and forth and bent it back and forth until it snaps and then touch it, it's really hot. You can burn yourself that way. The friction of the atoms inside of it heat it up. And so in Europa, you can calculate this. How much heat is being generated by friction by this stretching by the tides of Jupiter? It turns out it's a vast amount of energy. It's enough to melt the moon. There's easily enough heat being generated in there to maintain a liquid water ocean underneath it. That's why it was speculated. That's why Arthur C. Clarke wrote it into the 2010 book and movie, right? If you've watched those, there's a liquid water ocean under the surface of Europa. We know this. We've never seen it, but we've seen its effects. The surface of Europa has got these cracks in it. If you've ever seen a lake in Colorado freeze, maybe you have. It gets cold here in this state. I live on a lake, I've seen it. You get these sorts of patterns in it sometimes. They're not necessarily this color. This is actually, there's salt that is, the water under the surface of Europa is probably salty. And it may be leaking up to the surface and then evaporating, leaving behind salt. And then the radiation from Jupiter colors it into different colors. But also, flybys of spacecraft have been measuring the gravity of these moons, and they can tell by passing by them in different ways that there is a liquid water ocean under the surface. The ice is probably several miles thick. There's probably a core in the center of rock, maybe some metal. But the fact of the matter is the fact that there's salt on the surface means there is probably a rocky core that has minerals in it, and the water is mixing with it, making the water salty. That's why our oceans are salty. It's minerals from the rocks on the ocean floor that dissolve in the water. So that, a paper just came out showing that the salt on the surface of Europa is sodium chloride. It's table salt, like our oceans. It could have been magnesium chloride, it could have been all these weird things. It's like, no, it's actually salt, like our oceans. And it's mixing with the bottom of the seafloor, which is what our oceans do. And we know that the core of Europa is hot, heated up by tidal friction. And it may have cracks in the surface where heat comes out and blows out of vents on the seafloor, which we have on Earth. And when you look at the vents on the seafloor of Earth, there are tons of life there. These weird tube worms that come out, really creepy looking things. And there are lots of animals that have adapted, and plants that have adapted to the very hot conditions and the high pressure conditions near these vents. For my money, this may be the best place to look for life in the solar system. So, is Earth special? Maybe not. Maybe if you're having liquid water on the surface, yeah, but having liquid water under the surface, Europa's got to be. But is Europa alone? No! Let me show you Enceladus, the tiny icy moon of Saturn. Europa's big, Enceladus is small. Again, to bring up our home state, it's roughly the size of Colorado. It is extremely reflective, very shiny white. My fat fingers here, here we go. And it's got these long cracks near the South Pole, and those are spewing out water. The Cassini mission saw these. When you look at Enceladus with the sun behind you, or the sun behind the moon, the geysers of water are backlit by the sun, which is over here someplace. And you can see the shadow of the moon itself cast on the geysers. The surface of Enceladus here you're seeing is from reflected Saturn light. How romantic is that, right? The sun is lighting up Saturn. Here's this gigantic bright planet in the sky of Enceladus illuminating the ground. So this is literally the dark side of Enceladus here. This is the side facing. So the sun is on the other side. Saturn's over here, shining on the side. And this is the side facing away from Saturn, and is currently away from the sun. So you don't see it as well. So we know that's water. Cassini flew through that, found it was water, also determined there were organic molecules in it. Now, not necessarily life, but carbon-based complex molecules. So something is going on in the oceans of Enceladus that is very interesting. Are there fishies swimming down there? Maybe, maybe. I would give this number 2 past Europa. I'm liking Europa a lot more recently than Enceladus, but either one of these would be fine for life. Well, if Jupiter has a moon like that, Saturn has a moon like that, are there other moons like that? The answer is yes. Yes, yes, yes. These are all moons of Uranus and Neptune, including Triton, the cantaloupe moon. Looks like a cantaloupe. Triton also has these black spots on it. We think those are geysers of dusty, dark material coming out from the interior and blowing. It's a very, very thin atmosphere, and the winds are blowing it in these streaks across the surface. All of these moons, we believe, have liquid water under them. There are also these Kuiper belt objects, which we don't have very good pictures of because they're small and really far away. We think these may have liquid water under their surface as well. And then your friend and mine, Pluto. Turns out Pluto may have liquid under its surface. The heart-shaped region here, Sputnik Planitia, this western region called Tombaugh region, named after Clyde Tombaugh, who discovered Pluto. I remember sitting at my computer waiting for the press conference. Come on, Alan Stern from Southwest Research down in Boulder. Let's see these pictures. They displayed a picture of that, and literally the hair in the back of my neck stood up, and I'm alone in my room, and I exclaimed, "There are no craters!" And then one of the scientists went, "You see there are no craters there?" And I was like, "Yes, I just said that!" That's super important because an object out in this part of the solar system should be slammed with craters, and it's not. And that means that something has been smoothing over the surface, which means that something liquid is bubbling out from the interior and smoothing over the surface of Pluto. It has probably, liquid nitrogen is sort of like toothpaste, is what Alan said. That's the consistency of it. But it may also have a layer of liquid water underneath it, even though it's that far from the sun. Radioactive material in its core may be enough to heat it. Or it's possible it suffered a massive collision a long time ago, which formed its weird moons. That's a whole other talk. And the heat left over from that collision has kept the interior hot long enough for this kind of thing to happen. Either way, Pluto, dinky. Pluto's smaller than our moon by a long shot, and it's 3 billion miles out from the sun. It has liquid water under it. So Earth is not looking too special. Really? Water? Water? Can there be anything else that we could look at? Saturn has this gigantic moon Titan. It's about as big as Mercury. If Saturn weren't there, we would probably call Titan a planet. It has an atmosphere. The atmosphere is 50% denser than ours. It's mostly hydrogen, or excuse me, nitrogen, like our atmosphere is mostly nitrogen. But it's cold there. It's like, I don't even know, 4,000 degrees below zero. I don't know, I'm making that up. It's like, it's I want to say 200 degrees below zero. It's cold enough that water is frozen into ice so hard that it's like granite is here on Earth. So it's really, really cold there. But, I should say and, not but, the atmosphere is hazy, and it's hard to see through with visible light. When you look in infrared light, it can get through that atmosphere, and you can start to see the surface. Cassini had an infrared camera, started mapping the surface. It also had radar. So as it's going over the moon, it was bouncing radar off the moon's surface and letting that bounce back to get topography. So you know how long it takes a signal to come down and go back up. You can tell if you're hitting a valley or a mountain or something like that. And near the North Pole, it found these weird regions. This is a radar map. It's not a picture. It's actually from radar returns, where something there was not reflecting radar. It was very dark. Not reflecting radar, everything reflects radar unless it's really, really smooth and liquid. And it's like, oh, is this a lake? And the answer is yes. We now know that this is a lake. It is liquid methane. Cold enough there to have methane be a liquid. And you can see, I mean, of course it's a lake. Look at all these tributaries. These are rivers up in the hills, the highlands, flowing down and feeding this lake. And they've seen changes in it. The radar, as Cassini would wait a year or two and then pass by Titan again and take radar measurements, you can see changes in the lake that are clearly shows it's liquid. Yeah, it's cold there, but we know that life on Earth is carbon-based. Here's a lake full of carbon, methane and ethane. It has rivers flowing into it, which means methane must be evaporating and then blowing around in the atmosphere and then raining down in the hills to fall back down onto that lake. That's the water cycle, fellow babies. That is what's happening on Earth just with methane. And it's got all that organic material to work with. This is why NASA is sending a quadcopter to Titan. Did you read about this yesterday and today? Yeah. Anybody read my blog about it today? Mm-hmm. A nuclear-powered 4-propeller, actually 8 propellers, Fort Arizona, rover that will land on Titan, look around, sample some stuff, and then say, I'm going over there now, and it's going to lift off and fly 8 or 9 miles, something, or 5 miles, something like that, and then land and do it all again. And it's going to hop around Titan this way. Titan has 1/7 the Earth's gravity and a thicker atmosphere, so it's actually easier to fly. If you had wings, you could fly on Titan, but of course you'd be frozen solid and you would die. So for 4 nanoseconds, we'd have a lot of fun. So again, Earth, special? Depends on what you mean by special, doesn't it? One more thing about all this. Kepler 1625 is a very interesting star. This was observed by Kepler. It has a planet, Kepler 1625b. Here's a transit curve for it. I think that's parts per thousand. So these are millimags, if you care. But you can see the huge drop by the planet. Clearly something going on here. But then what they found was, what's this? That's interesting. Why would there be a second dip? And David Kipping, a guy, you can follow him on Twitter. He's the one who did these observations. But that could be a moon of this planet. This planet's been observed 3 times in transit, and every time this dip shows up, and it's in a different place. One time it's here, and one time it's over here. That's what you expect, right? You have a moon going around a planet, and it's over on this side, so it transits first, and so you get a dip first. And then some orbits later, maybe it's like right here, and they transit together. And then some orbits later, it's behind the planet and transits later. So you see that same dip moving around. Could this be the first exo-moon found? And I've looked at the data, I've read the papers, and I'm like, oh, you're so close. It's almost there. I think this will pan out, but we don't know yet. We can't say for sure. The problem is, Kepler 1625b is about the size of Jupiter, and the moon would have to be the size of Neptune. That's a big moon. that's a big moon. It won't be habitable, because it's going to be like Neptune, right? However, moons don't have to be that big. Jupiter's got all these small moons. What if Jupiter orbited where Earth is? Europa would be liquid. It would be a big old water droplet sitting there orbiting that planet. By the way, Europa has more liquid water under its surface than Earth does on its surface. You may have seen that graphic of a dry Earth with the water droplet next to it showing all the water, and Europa next to it actually has more water. So there's actually more room for life on Europa than there is for Earth as far as water goes. And so that could be the case here as well. We don't even have to look at planets. We can look at moons and start looking for life. Again, it's not looking so special for Earth. Oh yes, one more thing, just very briefly. Mars, not very Earth-like, small, dry, cold, right? Now it's small, dry, and cold. A long time ago, we know it had water on the surface. There's plenty of evidence for rushing water. There are river and lake beds. The Curiosity rover landed in Gale Crater, which is like 90 kilometers across. It's this massive crater, specifically because we knew it was a lake. There is clay in the ground there, and clay forms in water. When Curiosity landed and took pictures, it looked like freaking New Mexico. Just you see red and white layers of sediments that had been deposited by a lake over year after year after year. Incredible. So you could look at a planet now and say, well, there's no life on it now, but there might have been 2 billion years ago. Or you could look at a planet now and say, there's no life on it now, but in 1 billion years when it cools off or whatever, maybe it will. So planets in the habitable zone, good. Not too many Earth-like planets, bad. lots of moons that could have water under their surface, good. Maybe we don't need water, bad. And I mean this, and I'm switching back and forth because it depends on what you're looking for. If you're looking for life, this is all great news, right? Everywhere we look, we're seeing conditions that could have life. The problem is, it's not making Earth look very special. But is it? Is that fair? In 3 weeks, we have the 50th anniversary of Apollo 11 landing on the moon. In 1968, at Christmas time, Apollo 8 circled the moon and saw the Earth like this over the edge of the moon. It actually saw the Earth rise, because as they were orbiting the moon, their geometry changed, and they could see the Earth rising over the horizon. I love this picture. It's been remastered. Beautiful, beautiful photo. This is a very famous picture. There's also the picture taken of just the Earth, the color photo of the Earth from space. These pictures sparked the environmental movement of the 1970s because we saw the Earth hanging out there in the black of space and clearly special. It's the only planet in the solar system that is blue-white like this because of water. I love this picture. I have nothing but praise to say about it. But it's not my favorite picture of the Earth. This one is. This was taken by the Rosetta probe, the European Space Agency probe that went to the comet 67P Churyumov-Gerasimenko. You're all familiar. 67P Churyumov-Gerasimenko. I practiced saying that so many times. I'm going to keep saying it because it's awesome when people say it. 67P. They also call it Chugu. I like that too. Churyumov-Gerasimenko. It was a gravity assist from the Earth to get out to this comet, and it took this gorgeous picture. The sun's way over there. You're looking mostly at the dark side of the Earth. I love this picture because we're used to seeing the moon this way. Venus, Mercury maybe, but not the Earth. I mean, the Earth is like this all the time, just like any other planet, but we don't see it this way. You have to be in space to see it this way. And I love it because it's familiar, right? Here's the ocean, look at that color. And you can see the clouds and the water, and some of these images you can see Antarctica. Matter of fact, that's not Antarctica, it can't be Antarctica, it has to be here. But you're seeing this water-covered planet, but you're seeing it as an alien world. You're seeing it from space. This is maybe more like what an alien or what humans will see when they're putting bases on the planets and coming back to Earth. And that's why I love this picture. It's both familiar and alien. That's it. That's us, right? This is a planet where we've evolved and we've adapted to the atmosphere, the water, the temperature, the chemicals, the other life around it. We can't live on Mars. We can't live on the ocean in Europa, not without a lot of help. We certainly couldn't live in the methane lakes of Titan. And we'll find other planets. We will. I asked a friend of mine who studies all this, how many exoplanets have we found at the size of Earth in the habitable zone? And she said it depends on who you ask. She thinks it's like 9. Other people say 20, because we don't really know how big these are. And these aren't necessarily Earth-like planets. They could be like Venus, or they could be loaded with chlorine or something, and they're uninhabitable. We're not going to find that many planets like Earth. But we are going to find a lot of planets like Earth. I love saying contradictory things, right? They're going to be like Earth. They may have liquid water on the surface. They may have 78% nitrogen atmosphere, 22% oxygen. They may be like, if you're a fan of Stargate, they may always look like British Columbia. Okay, you're laughing, okay, Stargate fan. Every planet they go to looks like British Columbia. It's because that's where they filmed it. We may find it, but they're always going to be different. There's always going to be something about them that isn't Earth. We may find billions of Earth-sized planets in our galaxy. That's the prediction. Billions. There are more planets than stars in our galaxy. We know this now. But how many of them are going to be Earth-sized? How many are going to be Earth-like? And those numbers get smaller and smaller. And then how many of them are Earth? That's 1. And it turns out, if you ask the question that way, is the Earth special? The answer is yes. Thank you. So it's like 11 o'clock. So
9:40.
Is that like an hour? It's 9:30. So I think that range is an hour. So that's good.
Yeah, you did well. You did really well.
I can take questions if you want, Or if y'all want to clear out, I understand that impulse too. Yes? I guess the answer is yes, I'll take it.
I have one. So, like, our solar system is 8 planets. Are there any other planets that have been found that are suspected to be part of the larger system, or is it all one planet, one star? Or do we know that?
Oh, well, like HR 8799 that has 4 planets already. Is that what you mean? Are there other solar systems like ours?
Yeah.
It turns out yes. We've found many multiple planets. There are lots of C, D, E's, and F's, and even G's. Most people, their favorite is TRAPPIST-1. Do you remember hearing about that? That was in the news a lot. This is a dinky little red dwarf star that has 7 Earth-sized planets orbiting it. And 2 of them are in the habitable zone. 1 is near it. They're unlikely to be like Earth. But this is really awesome because it turns out we think that M dwarfs. Oh, thank you. Thanks for coming, and thanks for laughing at my joke earlier. It turns out red dwarf stars preferentially make smaller planets than bigger ones. So you don't tend to see Jupiters around M dwarfs. You see Earths or Earth-sized planets. A friend of mine says we should call them Venus-like planets because people when they hear Earth size. They think, oh my gosh, it's Earth-like. And it's like, no, it's not like the Earth, it's just our size. Venus is our size, so we should call them Venus-sized planets, and that'll keep everybody from thinking about it. But TRAPPIST has 7 planets like that. They're all huddled really close to the star. But it's a complete solar system. Also, the cool thing about it is it's 2 billion years older than the sun or something like that. So if there is life on those planets, they're 2 billion years advanced of us. Or gone already. They've converted to energy like every science fiction story tells you we've evolved to a higher form of consciousness. And they've all moved to Boulder, apparently. But the really cool thing is that M stars are far and away the most common in the galaxy. 75% of all stars are these little red dwarfs. And red dwarfs love to make Earth-sized planets. So it's entirely possible that that graph I showed you was wrong, and Earth-sized planets dominate by far. The problem is finding Earth-sized planets around these M dwarfs is hard because they're so faint that even close ones are hard to see. I mean, Proxima Centauri has a planet. It's the closest star to the sun, and we just found it. And if you look at the paper, the data is ratty as hell. It's really hard to see the planet in there. So, M dwarfs, they may all have planets like Earth. We don't know. It's very exciting. Yes?
So if you say Travis has lots of planets around it, Venus size, pretty close together.
Super Mercuries. Yeah.
I'm thinking interactions between these brothers and sisters going around. But I suppose that's also happening on Saturn. So
yeah, you get these resonances. As the planets orbit the star, they interact gravitationally. And chances are, especially in a system that close, there were probably a lot more planets at first, and some of them got tossed out of the system. In fact, when you look at models of our solar system, the only way to get Jupiter, Saturn, Uranus, and Neptune the way they are now is if there had been a 5th gas giant back in the day that got ejected. We know that Jupiter and Saturn moved in, and then Saturn basically put the skids on that and pulled Jupiter back out. We're pretty sure that happened, depending on the models you look at and everything. But the only way you get that system to work out is if there was a 5th planet to do some other stuff. But there's no 5th planet now. Where is it? Out in the galaxy.
do we know where it is in radius?
I don't know. I think there were just a bunch of models. What they do is when they do these models, they give it a bunch of initial conditions. In other words, here's a planet with this mass, this distance from the sun, and all that. And they do that for a bunch of planets, and then they run the model, and then they change everything a little bit and run it again. They change things a little bit and run it again, and then you get statistical answers. So 75% of the time, you need a 5th planet in there to get our system to look like it does now, which is pretty good. So yeah, the TRAPPIST system may have ejected a bunch of planets, but in the end, a lot of the times, the planets wind up in these resonances. So for every 2 times this planet orbits, this one goes around once. And it turns out the gravity interacts to force that to happen. 3 of the 4 big moons of Jupiter are like that. They're in a 1-2-4 resonance. So the inner one goes around 4 times, the next one goes around twice, and this one goes around once in the same time. And they kind of tug on each other to make sure that happens. It's a stable way of orbiting. And so I imagine when we look at these TRAPPIST-like systems, they're all going to be in residences. Because if they weren't, they would be chaotic and they wouldn't last very long. Because these planets get really close. Somebody did the math and said, yeah, if you're standing on one of them, 2 of those planets would show disks to the naked eye, which is awesome. Because Venus is just 1 arc minute across when it's between us and the sun. And the problem is it's close to the sun in a crescent. So it's really hard by your eye to see it as a disk. But apparently from TRAPPIST you can see 2 planets that way. Imagine how quickly their astronomy would advance. If they weren't being cooked by flares from their star, which is another issue.
Very dizzy, yeah.
What, they get a hangover, right? TRAPPIST?
Yeah.
Great beer.
Oh yeah, and their year is like a week. So getting telescope time on Hubble is like really super easy. They're putting out calls for observations every 7 days. Yeah, you don't have to wait 6 months for Orion to rise, basically. You just have to like, yeah, there it is. Right, you got it. It'd be really weird.
Great.
Any other questions? No? Okay, excellent. Thank you again.
Thank you, Bill.